Shall we get started? Again, our topic is still movement of matter energy through an ecosystem, but our focus today is going to be the movement of energy. And you're going to show your knowledge of the movement of the energy through the ecosystems, and we're going to get a little bit deeper on that one. But to start off with, I'm going to ask you the question, what is the 10% rule? Correct. The 10% rule is that 10% of the energy within a trophic level, such as of the producers, will move up to the very next trophic level. In terms of producers, 10% of that will move up to the primary consumers. So if you have 100,000 joules of energy within the producers, 10% of that, or 10,000, will be available or moving up to the primary producers. Now, for today, what I want to do is go over the calculations that you need for the analysis interpretation. That is calculating the rate of the chemical reaction. And you're going to find that you know this because you've done this before. And I want to go over this because I definitely had a few questions over the past few days on how to do this. Then we're going to go over gross and primary reactivity. So we're going to look at another worksheet that will dive a little bit deeper at what we looked at in terms of movement of energy. And you're going to see where the energy actually goes. So not all of it moves up. What happens to it? It's going to get that a little bit more this time. So if you remember our photosynthesis, that general equation was carbon dioxide is going to react with water in a plant in the presence of light. It's going to produce glucose and oxygen. And in the lab, you just kind of looked at the product being formed and you knew that you're going from the reactant to the product. But in truth, photosynthesis has several reactions that occurs. I have the light hitting the chlorophyll P680. It's going to cause enough energy to split water into oxygen and hydrogen. And an electron is going to move to a protein called PQ. And then it's going to move further into cytochrome, moving further to another system called photosystem 1. Yes, there are several steps to this. And question is, do you need to know every single step to understand the overall process of photosynthesis? Well, something I want to introduce to you. That is called Hess's Law. Hess's Law allows us to look at just the reactants, initial molecules, and the products, the final molecules. And what Hess's Law states, and please write this down, states that the overall change in energy is the sum of all the reactions from initial reactants to the product. And I can also use Hess's Law in terms of the overall rate of reaction is going to be the sum of all the reactions within that process from the initial reaction to the final reaction. So make sure you're writing Hess's Law down. And what this allows us to do is, from the point of view of our lab, I can look at here's how much oxygen I had in the beginning, here's how much oxygen I had at the end, and how much energy changed to make that change occur. And that will tell me how much energy is used or made by photosynthesis, used or made by cellular respiration. Are we ready to move on? Okay, let's look at how to calculate a rate of change. So if you remember this table from our lab, we had time that you're supposed to write down, time in 1 minute. In this case, I'm borrowing some data from one of the groups. We have 8.1 milligrams per liter of oxygen. 60 minutes, we had 8.4 milligrams of oxygen per liter. In 31 minutes, we had 9 milligrams of oxygen per liter of water. So how do I calculate the rate of reaction? How do I do the analysis interpretation? Well, I start off with this general equation, which is the rate's going to equal the change in oxygen, milligrams per liter, over the change in time. And that Greek symbol delta, that represents a change. And I can break it down to something that may look familiar to you, may look similar to something you saw and used last year. Yes, I have concentration final minus concentration initial divided by time final minus time initial. Now I just plug in my numbers. I'm going to use the 16-minute one for this example. We're going to use a 31-minute one later to see if you know how to do the procedure and the calculation. So let's plug in. Final concentration is 8.4. Initial concentration, 8.1. Our final time, 16. And our initial time, 1. Let's plug those numbers in there. And then let's do a little bit of math. 8.4 minus 8.1 is, 0.3, and 16 minus 1, 15. That brings us to the next step. Now we just do the division. Now, I do have a question for you. Are we going to do this calculation in a way that, let's say, Hard Dog's feeling a little lazy today? Yeah, I'm just going to use my calculator. Or I'm going to go for it. This is the best calculator I can use. Let's see which one to use. What is 0.3? I'm going to use my brain here, divided by 15. And what I love about this number is I've got both numbers divisible by 3. So I've got 0.1 divided by 5. Oh, what is 1/5? How do I deal with the point? Got an answer there. Good job. 0.02 milligrams of oxygen per liter per minute change. That's the change I have. Does this equation look familiar to you, by the way? Velocity equals change over distance or change over time? Yes, it's the same equation that we just used. So the equation for velocity is the same as rate. In fact, a change for velocity is a rate change. What's the rate of your walking? What is the rate of you running? What's the rate of the car moving? Same calculation. Okay. Now, pull out your worksheet for the day, and we're going to go over a couple of definitions. You don't have to write this down, but I do want you to listen, pay attention, and definitely participate. Think about this a little bit. If there are a couple of things you want to write down, just to remember, you can, but the definition is in your worksheet. But first, we're going to look at the productivity of ecosystems. Now, much of this was actually borrowed from economics. So in economics, we have something called a gross primary productivity. This is usually considered used for the country or a corporation, a company. But for this example, I'm going to use a paycheck, something simple. And this is, in terms of your paycheck, total amount of your paycheck. For example, you, in terms of your earning, you're earning $3,000 a month. That's what's on your paycheck, your gross pay. But is that what you're able to spend? Is that what you take home? No. What you have is the next piece in this called the net primary productivity. This is the amount after all the essential things we have to spend on, that we have to use things on. So after deducting healthcare, after deducting taxes, federal taxes, California taxes, city taxes, if you own property, property taxes, then what do you have left? Then you have the net primary productivity. So that is the gross primary productivity at $5,000 minus healthcare, minus taxes. In other words, $3,000 minus $500 minus $1,000, leaving you with $1,500 to spend as you see fit. In biology and ecology, we just borrow this and change the definition. Now, look for this definition on your worksheet. The ability of producers to capture light energy and fix carbon in organic compounds. Circle that because you're going to have to go back to that for the first couple of questions on that worksheet. So I want to make sure that you know where it is. The next definition I'm going to go through is the ecology version of net primary productivity. Yes, it's going to be related to energy, not money. This is the amount of the gross primary productivity that the plant uses to grow. Add to its biomass after respiratory needs of the producers are met. Find that definition in there and circle it. You know, in mine, I added adding to its biomass, or that's within that definition. But if it's adding to its biomass, it's going to grow. That's what it's going to do. And again, what this is the net primary productivity minus, well, what do we have? Well, from the last worksheet, we know that we lose a certain amount of energy to heat, and we lose a certain amount to cellular respiration. So after I deduct those two things, that is what's left for the plant to use to grow, to use for its own needs. Okay. Now, what I want you to do next is work through and finish the worksheet. And remember, questions 1 and 2 are going to ask you about gross primary productivity and net primary productivity and the differences between the two. I want to walk around the classroom, and if you have any questions, speak up. We'll get through this worksheet together.